Today's lesson is 2.3 Atoms, Elements, and the Periodic Table. Today's lesson 2.3 Atoms, Elements, and the Periodic Table. So, some chemists, when putting together the periodic table, began recognizing patterns in properties and behavior of many of these elements. So, the following elements share many physical and chemical properties, but have different atomic masses. What I've included here are the alkali metals over on this side and the halogens on this side. So if you look at the periodic table, they are organized by similar properties and behavior of elements. So other sets of elements that display similar trends in their properties and behavior include the noble gases and the alkaline earth metals. Now, these similarities led chemists to search for fundamental properties that could be used to organize all the elements. So we have Dmitri Mendeleev in the 1800s who organized the periodic table as such. And if you look closely, you will see there are some similarities in terms of how he organized some of the common properties in elements. So Mendeleev organized the known elements in order of increasing atomic masses. So this table of elements was organized so that the elements with similar properties were arranged in the same columns. Now, because Mendeleev's arrangement highlighted periodic patterns of properties, he called this the periodic table because they were repeating patterns in property. Now, let's go into more modern times. And the modern periodic table is a modification of the arrangement that was first proposed by Mendeleev, which led to the arrangement of the elements according to the atomic number. Now, according to periodic law, the chemical and physical properties of elements repeat in a regular periodic pattern when they are arranged according to their atomic number. So the atomic numbers, or the periodic table, is organized by these atomic numbers. And we go from 1 to 2 to 3 to 4 to 5. That's that periodic pattern in which the periodic table is repeating. And that's what's referred to as periodic law. Now, electrons within energy levels. There is a limit to the number of electrons that can occupy each energy level. So we can fit 2 electrons in the first energy level. We can fit 8 on the second energy level. And for now, we're going to assume 8 in the third. But remember that this one is going to break the rules. In terms of Bohr and Bohr-Rutherford diagrams, yes, the third energy level will contain 8 electrons. But when we go into electron configuration in chapter 3, you will see that this isn't going to follow that pattern of 8 electrons in that third energy level. Anyway, moving on. So the periodic trends that result from organizing the elements by their atomic numbers are linked to the way in which electrons occupy and fill these energy levels. So there are what are referred to as pattern-based on energy levels and electron arrangements. And there are 2 patterns of relationships to look at when it comes to the arrangement of the periodic table. The first one is the period-related patterns. And the periods are, in essence, the rows on the periodic table. The groups, on the other hand, they represent the columns on the periodic table. So let's look at the period-related patterns. These are the rows. Okay, these are the rows on the periodic table. And you will notice that elements in period 1 or in row number 1 have electrons in one energy level. The elements in period number 2 or row number 2 have electrons in two energy levels. And if you look at it on the periodic table, there are 7 rows on the periodic table, which means that there are 7 energy levels on the periodic table to represent the 7 rows, or should I say now periods, on the periodic table. So an element's period number is the same as the number of energy levels that the electrons of its atom actually occupy. So let's look at this periodic table. So here are the 7 rows of the periodic table. You might be wondering what these are here and think that those are like an 8th or 9th row, but in fact, they fit right over here in case you didn't notice the atomic numbers. Okay, so they fit in there. So there are 7 periods or 7 rows to the periodic table, which mean they to represent the 7 energy levels. And for now, we're going to treat this as energy level 1, energy level 2, so which means that if we've got a second energy level, we have electrons on the first energy level as well. We've got the third energy level, fourth, and so on. And I'm not going to draw lines right through it because I know someone's going to, jump the gun and go into the electron configuration and how later on the way we number the energy levels differs. But we won't worry about that for now. Right now, we're going to treat it 7 periods at the periodic table, 7 energy levels where electrons will float around. Now, the next pattern is the group-related pattern, the groups. And the groups, as we mentioned before, are represented by the columns. So these go up and down. So all elements in each main group have the same number of electrons in their highest outer energy level. These are known as the valence electrons. So the valence electrons are the electrons found on their last energy level. So it's on their outer energy level. So in other words, if we are looking at an element on the third energy level, whatever electrons are on that third one are considered the valence electrons. The electrons found in the first and second energy levels are just there, and they're typically full. It's that third energy level for that particular example that is very important when it comes to chemical bonding. So in chemical bonding, it is the valence electrons that are involved. So they are responsible for the chemical behavior of elements. So these valence electrons are so important. So we are going to number the groups from 1 to 18. So there are 18 groups to number them. And so if we look at, they also represent the valence electrons. They don't fit this pattern for all of them, but for the most part, group 1, 1 valence electron. Group 2, 2 valence electrons. Group 3, 3 valence electrons. 4 after that. Then use my periodic table to kind of figure out the number of valence electrons from, because a lot of these in here are multivalent, and so they have the ability to lose a number of electrons. But anyhow, let's go and shift on over to 13, group 13, 14, 15, 16, 17, and 18. Now, the most that we can ever have is 8 valence electrons, ever. Okay, so if you ever end up somehow counting more than 8, then you're wrong. Okay, so it's got to go up to 8 max. It could have less, it could have 1, it could have 2, it could have 3, it could have 4, it could have 7, but it cannot have 9, cannot have 10, cannot have 11. Okay, there are some exceptions to that rule, as you'll see in actually in my lesson on 3.4. But anyhow, when we're looking at 13, 14, 15, 16, 17, and 18, the trick is drop the one that's in front. drop the 1 in front, drop the 1 here, drop the 1, drop the 1, drop the 1. So which means that all of these, okay, so 13 will have 3 valence electrons. So all of these will have 3 valence electrons. The next will have 4, 5, 6, 7. These are going to have 8, with this exception that will only be 2. You can argue with me on some of these, but for the most part, we're going to try to keep things really simple. You would typically want a periodic table with the oxidation numbers to get to understand that there are some multivalents also located within here. So please don't argue in the comment section. Moving on. Now, the significance of a full outer energy level. Okay, so the noble gases, group 18, so group 18, that's right here, they have a full energy level. Okay, so they are very unreactive, or as others will say, they are inert. Okay, they don't react. You don't typically see them in bonds. You don't see neon bonding with oxygen or with sodium or potassium. Now, chemists believe that having an full outer energy level must be very stable electron arrangement. So its outer electron level is unlikely to change because it's reached what is referred to as a stable octet. So when an atom reaches that stable octet, fills their outermost energy level, they reach this so-called stable octet. So for ions, in essence, ions try to reach this stable octet by either gaining electrons or by losing electrons. In covalent bonds, atoms try to reach this stable octet by sharing electrons. So here's some Bohr diagrams of noble gases. Notice, so here we have helium. Helium has 2 valence electrons. That's it. So notice, period number 1, 1 energy level. That was the one exception. Sorry, this should be, so we'll just take away that 1. So 8 valence electron, with the exception of helium that has only 2 electrons that can fit on that first energy level, right? That first energy level can only fit 2 electrons. This second energy level can fit up to 8 electrons. So here's an example of neon, which is the noble gas on the second energy level. So we have 2 electrons on that first energy level. We have 8 valence electrons on the, 2 electrons on the first energy level and 8 valence electrons on the outermost energy level. Argon here, right, number 3, and argon third energy level, so it'll have 3 energy levels, 1, 2, 3. First energy level, 2 electrons max. Second energy level can fit up to 8. And the last energy level, because argon is in group number 8 or 18, drop that 1 to give us also 8 valence electrons on that outermost shell. Last thing I want to outline, we saw the Bohr diagram, and I share about Bohr-Rutherford diagrams in an earlier lesson. But now, when it comes to bonding, we like to use what's referred to as the Lewis dot diagram or the electron dot diagram. So a Lewis dot diagram of atoms include the chemical symbol surrounded by the valence electrons that it contains. They do not contain, so do not pair the electrons until you begin to draw your 5th, 6th, 7th, or even 8th valence electron, and you'll understand what I mean when I draw these. So if you look for magnesium on the periodic table, let me get rid of some of this stuff here. So here's magnesium. Magnesium, they're group number 2. So it has 2 valence electrons. And notice when I draw the 2, I'm going to draw 1 here. I'm going to draw the second one here. What I want you to do when you're drawing these is imagine an imaginary square. And when you're drawing these electrons, you are drawing the electrons 1 per side. Actually, let's not do that. Let's not do that one. We're going to use that model here. Actually, no. Sorry, let's do it. I like to do it with oxygen here. And I'll explain it to you in a moment why specifically we're doing it there. So anyhow, if we look for oxygen, here's oxygen here. So here's group 16, and which means drop the 1. So 6 valence. So when we're drawing the 6 valence, we draw 1 per side. 1, 2, 3, 4. Okay, we've drawn 4, 1 per side. Now we start to pair. Now we can pair our 5th. You can pair it anywhere. So there's number 5, electron number 6. We're going to pair it there, let's say, and there we have it. There are our 6 valence electrons around oxygen. We don't want the lines to represent the that imaginary square, but the reason we do this is because, as you're going to see in 3.4, when we actually draw Lewis dot structures, these single electrons represent bonding sites. Okay, this is where a bond is going to take place, or this is where it's going to maybe gain an electron if it is a non-metal for an ionic compound. So that's the reason why we don't pair them up, because in essence, if we decided to pair those up, okay, so here's oxygen, okay, and we drew 1, 2, 3, okay, we know there's 6, so 2, 4, 6 electrons. Right now, everything is paired up. So by pairing everything up, we lose these so-called bonding sites, and there's nowhere now for us to try to make our bonds. So it makes bonding and drawing our structures, our Lewis dot structures, a lot simpler if we do this method that I outlined in this note. So let's do the electrons for carbon and for bromine. So carbon here, there's carbon, group number 14, so drop the 1. So there are 4 valence. So imagine that imaginary square. So there's 1, 2, 3, 4 valence electrons. And what's great here, using that method that we said, notice nothing is paired up, which means we have 1, 2, 3, 4 bonding sites. And one thing you're going to know when you are bonding, carbon has the ability to form up to 4 bonds around one atom of carbon. And let's look at bromine now. So here's bromine on the periodic table, group 17. So drop the 1. So there's 7 valence electrons. Oops. So 1, 2, 3, 4, 5, 6, 7 valence electrons, allowing us for 1 bonding site right there. So that's where it can bond if it's bonding in a covalent bond, or that's where the electron will be gained when a metal will give it up. So here are some practice problems that I have at the end of my my slides. You can view my slides with the answers to these practice problems on my website. Just click on the link below.
I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.